Hey Phyz kids, Campbell here. In our last video for our summer math assignment, we're going to talk about integral calculus. So just a little recap from the last video. Derivatives are just another name for slope. So when we were taking the slope of a position versus time graph to get our velocity graph, we were just taking a derivative because velocity is equal to the derivative of position with respect to time. So dx dt. And remember, d just represents a teeny tiny amount. And when we took the slope of a velocity time graph, we were just getting acceleration because acceleration is dv over dt. Now, if we go back to Phys 1, remember that we could also go backwards. If we took the area under an acceleration graph, we got velocity, because remember that the equation for area, right, is base times height. And so if we rearrange this equation to solve for our change in velocity, right, we get the change in velocity is a times t, or base times height. So when we have that sort of a format of an equation, something is equal to something times something, the area under those things gives us that whatever that equals. And same thing when we took the area under a velocity versus time graph, we got the change in position. Well, remember that integrals are just areas. So, that means they're the exact opposite of a derivative. In fact, integrals are called antiderivatives. So, let's just talk a little more about this. So, integration really is just fancy addition. We're just adding up all the space underneath the curve. So, for example, if here's my velocity graph, velocity versus time graph, and I want to know what my displacement is, say at t equals 9 seconds, whoa, we would just do this area up to 9 seconds, right? So area is equal to base times height. So our displacement is equal to the base, which is 9, times the height, which is 10, which is just 90 meters. Now, does that tell me where my position is? Well, no, because it's just the change in position. It depends upon where I started. If I started at x equals 0, absolutely. My position is 90 meters from where I started. But if I don't know where my initial position is, then I don't know where my final position is. So when we do areas, all I'm doing is I'm getting a change. How about this? If I wanted to know my displacement from this graph, this velocity versus time graph, well, in this case, right, we have two different areas we have to add together. We'll call that area 1, and we have here our area 2. Now, we've already calculated area 2, right? That's the same as above. I did that to make math a little easier. Here, right, this area 1 is a triangle, right? So the area equation for a triangle is 1/2 base times height. So 1/2, the base is still 9. The height here is this height, so that's 18 minus 10, or 8. So that would be 4 times 9, which is 36, plus our original, which is 90, which is 126 meters. So there's our displacement. Again, that's the displacement, or a change in position. But it is not my final position because I don't know where I started. So there's a limit when we do areas, in that we have to know where we started. Now, what about this? You'll notice in Phys 1, I never had you take the area under a curvy graph, right? Because how do we do that? We don't, what's the area under a curvy thing? Well, what if we added up, right? If integrals are just fancy addition, right? What if I made these into little chunks and I added up these little chunks? Well, the problem is, right, is I've got this little space here. So even if I added up all these little rectangles, I'm still missing that little smidget piece right there. Okay, well, what if we made teeny tinier rectangles? So we made them teeny tiny. So the smaller they get, right, the smaller this little extra area is. So if we think about that, then if the area of one strip is base times height, then The total area would be the area of all the stripes, which would be the sum of those rectangles. And if we made those teeny tiny rectangles teeny tiny, then the actual area of all the strips, we would say as the limit of h, which is our base, approaches 0, and we add up all those rectangles, right? Then we'd have teeny tiny, tiny, tiny rectangles. That would give us the actual area. And in calculus language, what we call that is the integral. So the integral of f of x times dx. Dx just is all those little pieces that we're putting together, all those little strips. Okay, so let's take a look. We have an acceleration graph, and the acceleration graph is just 4, right? And so we want to take the integral of 4, right? Which means we're going backwards. We're going to, our velocity graph, right? And so the area here, right, which would give us our velocity, 4 times 1, means that our change in velocity from 0 to 1 second is 4. And then at 2 seconds, right, now we have 4 times 2, which is 8. So our change of velocity is 8. So that equation then would be 4x. But that's only if our initial position, or initial velocity, was 0. What if our initial velocity was 4? Well, then the graph would look like this, right? And then that would be 4x plus 4. Or what if it was 8, and then it would look like that? Or what if it was negative 4, and then it would look like that? So how do I know where I started to make this graph? Well, we don't. So we need to add what's called C. So there's a certain amount of uncertainty anytime we do an area about where did we start. And so in physics, we just call this our initial conditions. So our initial conditions we have to add to our integral. Boy, that looks beautiful. So that we get an actual picture of our velocity. Now, let's take a look at x. So what would the integral of x be? Well, if we take a look here, right, we said that integrals and derivatives were the opposite of each other. So that means going this way is the derivative. Now, if you look at what we just did here, right, the 4x, right, this would be a constant, so just like a number, right? So in a derivative, that would be 0, and then this would be 4. So what would this be if we took the derivative of it would give us x? Well, it's not x squared, right? If we took the derivative of x squared, we would get 2x. So it's not x squared, but what if this was x squared over 2, right? Because then there would be a 2 here, and that would cancel. That would give us x. All right, so that would be x squared over 2. But again, plus c, that initial condition. What if we had x squared? What would that be? Well, that's going to be x cubed over 3. And again, plus our initial conditions. What if we have x cubed? Well, x cubed is going to be x to the 4th over 4. And again, plus c. So you notice this trend, this thing that's happening here that gives us a general equation for integrals. Now, one thing that you need to know is that n can never equal -1, right? Because if this was a -1, right, this would be 0, and that would be undefined. So n can't equal -1. But that's all an integral is. It's just the opposite of a derivative, and it gives us the area under a curve. So cool. So let's physics again. So here's that graphic from the beginning again. So if I rearranged this and I wrote it in terms of the derivative, right? Derivative dx over dt is equal to v, right? So if instead of putting the deltas, I put the d's when I rearrange this, right? I get dx is equal to v dt. So if I take the integral, right? When you do math, you have to do the same things to both sides. So we take the integral of the derivative is just that. And then this would be the integral of velocity v dt. Same thing here. And so this is really what our equations look like for position and for velocity. Velocity is the integral of a dt. So let's actually apply that to some physics. So let's say our function is 0. So there's no area under 0, right? So you add up all the zeros, you still get 0. But remember, we have to add our constant. So let's make up a constant. Let's just call it a. Why not? A, B, C, whatever. We're going to call it a. If we take an integral of a dt, right, that means we're going to add a t here. But we have to add our constant. So you know what? Let's call our constant v naught. Why not? We're just making stuff up, right? And then what if we take another integral? What if we take an integral of at times vo? Well, that would give us, so this is 1, right? So plus 1, we put it over 2. That gives us 1/2 at squared plus vot plus our constant, which is our initial conditions, which we're just going to call x naught because we like to. Huh. Wow. Interesting, right? The integral of acceleration with respect to time is velocity. The integral of velocity with respect to time is position. So we just went backwards. Before we started here, right? When we did our derivatives, we started here and we went this way. When we do integrals, we're just going the opposite way. So let's use this. So we want to write a displacement equation for the following velocity function. And then if x naught is 0, what is the position at 2 seconds? Well, first we're going to do our integral. So displacement is the integral, oops, why did I put an a? v dt. So we're going to just plug this in here. So our integral 3t squared minus 5t dt. And now we're going to do our integral. So we're going to add 1 to this. And so we get, sorry, if we add 1 to that, that's 3. So that means the 3 goes on the bottom. And then this becomes t over 3. Here we add 1, right? So that would be 2. So we put the 2 on the bottom, and that becomes t squared. Plus we got to add our constant c, which is our initial condition. So in this case, that's going to be x naught. And so that means that our position is t cubed minus 5/2 t squared plus our initial conditions, x naught. So we want to find out what is the position at 2 seconds. So we're just going to plug in here 2 cubed minus 5/2 2 squared, and it said our initial conditions was 0. This happens to be minus 2 meters, right? Because that's 8, that's going to be 10, so negative 2 meters. So we have our position from our velocity equation. All right, so that's called an indefinite integral. Then that's why we have to add that c, that initial condition, that constant. But there are also definite integrals where we want to know the area between two boundaries. And when we do that, for example here, we just want to know what the area is between a and b, then we write the integral sign like this, where we put the boundaries there from a to b. Now, here's an example. Here is an acceleration equation, and we want the change in velocity from 2 to 4 seconds. So those are our boundaries. So we want the velocity between 4 and 2 seconds. So that's going to be the integral from 2 to 4 of a dt. So for a, we're just going to plug in this equation. So our change in velocity is the integral from 2 to 4 of t squared plus 3 dt. So first what we do is we take the integral. So we add 1 to this and we put it on the bottom. So that's t cubed over 3. And then we take the integral of this. So that means we're going to add a t to that. And then we're going to put brackets around here and do 2. So we're going from 2 to 4, or 4 to 2. 2 to 4, but always a final minus initial. So basically what we're going to do is we're going to put the 4 in for the t. And then from that, we're going to subtract the same thing, but with 2. So we're going to do 4 cubed over 3 plus 3 times 4. And from that, we're going to subtract. 2 cubed over 3 plus 3 times 2. So that means that this here is, when we do this quantity, this is 33.3. When we do this quantity, it's 8.67, and that's equal to 24.63 meters per second. So that's a definite integral. We are just interested in the change in velocity between those two boundaries. All right, now, one thing you'll notice, we can ignore c when we have a definite integral. So there was no adding c because we're just looking between that specific time point. Now, you also get integrals on your equation sheet. So here's the one that we've already talked about. These are the other integrals you're given, but if you just go and look at the ones we had for derivatives, right, the integral is an antiderivative. So if we take the integral of an exponential function, it's 1 over the constant a, and then notice this is the same. And remember, when we did a derivative of a natural log, we got 1 over x. So if we have an integral of dx over x, then we get the natural log. And here's our cosine. The integral of cosine is sine, just like the derivative of sine was cosine. The integral of sine is negative cosine. So these are all on your equation sheet. So do some work on that worksheet. If you have questions, drop me an email.